1.5. More about electron arrangements in atoms. As you have seen in topic 1.3, in a simple model of the atom, the electrons are thought of as being arranged in shells around the nucleus. The shells can hold increasing numbers of electrons as they get further from the nucleus. The pattern is 2, 8, 18, and so on. Electrons in different shells have differing amounts of energy. They can therefore be represented on an energy level diagram. The shells are called main energy levels, and they are labelled 1, 2, 3, and so on. Each main energy level can hold up to a maximum number of electrons given by the formula 2n squared, where n is the number of the main level. So, you can have 2 electrons in the first main level, 8 in the next, 18 in the next one, and so on. Apart from the first level, which has only an S sublevel, these main energy levels are divided into sublevels called S, P, D, and F, which have slightly different energies. Level 2 has an S sublevel and a P sublevel. Level 3 has an S sublevel, P sublevel, and a D sublevel. For a more complete description of the electrons in atoms, a theory called quantum mechanics is used, which was developed during the 1920s. This describes the atom mathematically with an equation called the Schrödinger equation. The solutions to this equation give the probability of finding an electron in a given volume of space called an atomic orbital. The electron is no longer considered to be a particle, but a cloud of negative charge. An electron fills a volume in space called its atomic orbital. The concept of the main levels and the sublevels is then included in the following way. Different atomic orbitals have different energies. Each orbital has a number that tells us the main energy level that it corresponds to. The atomic orbitals of each main level have different shapes, which in turn have slightly different energies. These are called sublevels. They are described by the letters S, P, D, and F. The shapes of the S, P, and D orbitals are shown in figure 3. The shapes of F orbitals are even more complicated. These shapes represent a volume of space in which there is a 95% probability of finding an electron, and they influence the shape of molecules. The first main energy level consists of a single s orbital. The second main level has a single s orbital and 3 p orbitals of a slightly higher energy. The third main level has a single s orbital, 3 p orbitals of slightly higher energy, and 5 d orbitals of slightly higher energy still, and so on. Any single atomic orbital can hold up to a maximum of 2 electrons. S orbitals hold up the 2 electrons, as previously mentioned. P orbitals can hold up to 2 electrons each, but always come in groups of 3 of the same energy, to give a total of up to 6 electrons in the p sublevel. D orbitals can hold up to 2 electrons each, but come in groups of 5 of the same energy to give a total of up to 10 electrons in the D sublevel. The energy level diagram in figure 5 shows the energies of the orbitals for the first few elements in the periodic table. Notice the first main energy level has only an s orbital. The second main level has an s and a p sublevel, and the p sublevel is composed of 3 p orbitals of equal energy. The third main level has an s, p, and d sublevel, and the d sublevel is composed of 5 atomic orbitals of equal energy. So each box in figure 5 represents an orbital of the appropriate shape that can hold up to 2 electrons. Notice that 4s is actually of slightly lower energy than 3d for neutral atoms, though this can change when ions are formed. Electrons have also a property called spin. 2 electrons in the same orbital must have opposite spins. The electrons are usually represented by arrows pointing up or down to show the different directions of spin. Remember that the label of an atomic orbital tells us about the energy and shape of an electron cloud. For example, the atomic orbital 3s means the main energy level is 3, and the sublevel, and therefore the shape, is spherical. There are 3 rules for allocating electrons to atomic orbitals. 1. Atomic orbitals of lower energy are filled first. So the lower main level is filled first. Within this level, sublevels of lower energy are filled first as well. Atomic orbitals, number 2, atomic orbitals of the same energy fill singly before pairing starts. This is because electrons repel each other. And number 3, no atomic orbital can hold up more than 2 electrons. The electron diagrams for the elements hydrogen to sodium are shown in figure 6. A shorthand way of writing electronic structures is as follows. For example, for sodium, which has 11 electrons. 1s2, 2s2, 2p6, 3s1. Note how this matches the simpler 2-8-1 used at GCSE. So 1s2 means there are 2 electrons, 2s2, 2p6 means there are 8 electrons, and 3s1 means there is 1 electron in each one of those levels. Calcium with 20 electrons would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, which matches 2, 8, 8, 2. Notice how the 4s orbital is filled before the 3d orbital because it is of lower energy. After calcium, electrons begin to fill the 3d orbitals. So vanadium with 23 electrons is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. Krypton with 36 electrons is 1s2, 2s2, 2p6, 3p6, 3d10, 4s2, 4p6. Sometimes it simplifies things to use the previous noble gas symbol. So the electron arrangement of calcium, Ca, could be written as brackets argon, brackets closed, 4s, as a shorthand for the brackets 1s2, 2s2, 2p6, 3s2, 3p6, brackets closed, 4s2, because 1s2, 2s2, 2p6, 3s2, 3p6 is the electron arrangement of argon. You can use the same notation for ions. So a sodium ion, Na+, would have the electron arrangement 1s2, 2s2, 2p6, one less than a sodium atom, 1s2, 2s2, 2p6, 3s1.